Let us look at chemical properties of second group elements. Again, we'll see the all list from beryllium through magnesium, calcium, strontium to barium. Beryllium, same way as lithium in group number 1, occupies special position. It reacts with oxygen, making beryllium oxide. This compound, when it is powder, is highly toxic on inhalation, leading to chronic berylliosis, a disease of the lungs, and cancer. This is amphoteric compound. It can react with bases to make berylates, K2BO2, and several different compounds, in which beryllium is always surrounded by 4 oxygen atoms. We have seen that coordination number of beryllium usually is 4. All other elements react in somehow similar way with oxygen, but this reaction is far more violent. Magnesium can burn in oxygen very easily. Calcium will react even at room temperature, same as strontium. Strontium can make not only oxide but also peroxide, and barium makes mostly barium peroxide. We practically never obtain these oxides directly by reaction of metal with oxygen. Most common synthetic reaction is decomposition of carbonates. So calcium carbonate decomposes into calcium oxide and CO2. All others do exactly the same. This reaction requires heating to temperature at around 800–900 degrees Celsius. All these metals react with water to make hydroxides and releasing hydrogen. Magnesium reacts with water only when it's powdered, but calcium, strontium, and especially barium will violently react with water even at bulk if you put a chunk of metal. Again, in each case you have hydrogen gas released. Similar reaction goes with oxide. Oxide reacts with water to make magnesium hydroxide, calcium hydroxide, which is partially soluble in water, strontium hydroxide, and barium hydroxide. We never receive beryllium hydroxide by this reaction. It is amphoteric and usually is precipitated by addition of sodium hydroxide or ammonia to aqueous solution of Be2+ ion. Beryllium hydroxide is practically insoluble in water. Magnesium has visible but very small solubility. Calcium hydroxide has solubility of around 1 gram per liter, and strontium and barium have visible solubility, so you can prepare, say, 0.1 molar solution of barium hydroxide in water with no problem. These all hydroxide react with acid to make salt and water. They also will react with acidic oxides like CO2 or SO2 or SO3 or NO2 to make corresponding salts and water. These reactions are of very special importance. Calcium hydroxide is known for thousands of years, and it has specially name in English as a lime. This is an old spelling with Y, as sometimes we say hydrated lime, quick lime. And historically it was the first mortar. When you put a layer of calcium hydroxide with some admixture of sand and I'll put bricks on it, with a reasonably short time carbon dioxide from air will react to make solid calcite, calcium carbonate, and water. As a result, you are making literally a rock between two bricks. This was very convenient reaction, however, is very slow. That's why construction in Middle Ages and in ancient time was fantastically slow. You cannot build more than a couple of feet, and then you need to wait for months for this reaction to complete 100%. Still, it was fantastic advantage over the first mortars existing. This mortar was replaced around 2000 years ago with silicate-containing mortars that we name cements and concretes. We'll talk about that when we'll go to silicates. Beryllium hydroxide solid reacts with hydrochloric acid to make beryllium, salt, and water. Beryllium ion in water has 4 water molecules surrounded it in tetrahedral fashion, as it should be, for maximum distance between each ligand atom. So that's what we have in acid. At neutral pH, beryllium hydroxide will precipitate B2 plus 2 sodium hydroxides, making solid BOH2 and 2 sodium ions released. This hydroxide can in turn be dissolved in excess of sodium hydroxide to make BOH4 2 minus ion and 2 sodium ions. And this would be cartoon of this BOH4 2 minus ion in sodium hydroxide. Such compounds, such hydroxides, we name amphoteric. Why only 4? The reason is B2 plus ion is very small. It's 0.27 angstrom. You cannot have more than 4 oxygens around such a small ion. Magnesium is slightly larger, and you can put 6 waters around. Magnesium, like other metals of second group, react with nitrogen to make nitride, Mg3 and 2. All metals of second group react with halogens to make appropriate salts. Calcium react with chlorine to make calcium chloride. But if you really want to make such a salt, you will not react metal with halogen. You will do reaction of metal with acid, like Mg plus HCl. You'll make magnesium chloride and hydrogen. These metals can react with carbon, making so-called carbides. For synthesis, it's more convenient to start with oxide. Calcium oxide reacts when heated with graphite, carbon, to make calcium carbide and carbon monoxide. Calcium carbide, in fact, is not carbide. It has no C4- ion. Instead, it has C22- ion. And they're sitting in crystal cell resembling sodium chloride, but instead of chlorine you have C22-. And of course, because of that, crystal structure is slightly distorted. This compound is specifically interesting because it reacts with water to make lime, calcium hydroxide, and acetylene or ethene, HC triple bond CH, which is very nice starting material for many of organic synthesis, and it is also a good fuel for many processes, giving very high temperature flame. Calcium carbide can react with nitrogen at high temperature, making carbamide, which is a good fertilizer. Among other salts, very special are sulfates. Magnesium sulfate has very good solubility in water, but calcium sulfate has very limited solubility. This number depends on crystal structure of calcium sulfate, and we have several of them. There is anhydrous calcium sulfate. There is calcium sulfate with 2 calcium sulfate units per water molecule, and there is gypsum, which has 2 water molecules for each calcium atom. Gypsum forms fantastically beautiful crystals that grow in caves because of this limited but visible solubility. So you can see these fantastic crystals, or these so-called gypsum flowers in caves. There are plenty of uses of calcium sulfate for engineering purposes, as well as medical. Other insoluble compounds of second group are phosphates. These materials contain calcium combined with usual phosphate, dihydrogen phosphate, or monohydrogen phosphate ions. Usually we do not have just PO4 3-. It can also have some additional ions. So our bone material is calcium phosphate of such a formula with a mixture of calcium carbonate. Our dental enamel is a very similar mineral, still being calcium phosphate of slightly different composition. Among other insoluble salts of second group elements are oxalates and chromates. So making a summary, who is insoluble for second group: carbonate, sulfate for strontium, barium, phosphate for calcium, strontium, and barium, and some of magnesium, and oxalates. Hydroxides are insoluble for magnesium only.